Hi, everyone. I'm Rebecca Wright, Chair of Computer Science at Barnard, and thanks for being here for our Computer Science seminar. We are delighted to have Victoria Dean with us today. Victoria is an assistant professor of computer science at Olin College of Engineering. She completed her PhD in robotics at Carnegie Mellon University in 2023. She was an NSF Graduate Research Fellow as well as a Siebel Scholar. And she works on reinforcement learning applications, both in robotics and building energy optimization. And she will be talking to us about that work today. Victoria, the floor is yours.
Great. Thanks, Rebecca. Great. Thanks everyone for being here today, both in person and on Zoom. Really excited about this visit to Barnard today. I figured I would start by talking to you a little bit about myself outside of research. So, let's see. Go note clicker. Oh, here we go. So I really like knitting and other fiber arts. That's a scarf that I made for a friend of mine. I also really enjoy swing dancing and other social dancing. Convincing people to do group costumes with me. So that's me with my building energy teaching team there, and also eating Ethiopian food. So if anyone else likes Ethiopian food and has recommendations around here, please let me know afterwards. On a more serious note, I really like teaching. Teaching is why I'm in academia. And in particular, I really like developing courses where students get to work on real-world projects. I think real-world projects can illustrate why students should care about their work and help teach students skills that are required beyond the classroom. So this is a course called Code for Good that I developed when I was an undergraduate at MIT. It gave computer science students an opportunity to work on real-world projects in collaboration with Boston nonprofits that wanted the chance to receive free technical consulting. I'm really proud of Code for Good because it still exists today, about 10 years later. It's now in its 10th year, and about 60 nonprofits have worked with Code for Good with MIT students, and hundreds of students have participated in the course. Now, as a professor at Olin, I'm the faculty advisor for a similar effort at Olin called PINT, which is Public Interest Technology, where students are working, again, on teams with local nonprofits doing computing and engineering projects. Another aspect of real-world projects that I think is really interesting is curricular integration, specifically around ethics. There's a framework that I developed for a course when I was in grad school at Carnegie Mellon called Ethics and Robotics, where my students were developing integrated ethics content for other computer science courses at CMU, developing ethics materials that are tailored to that specific course with suitable rubrics, activity design, and assignments. And I wrote a paper about this ethics integration framework, which I presented at SIGSI a couple years ago. And when I started at Olin, I wanted to continue that type of integration framework. So I developed an artificial intelligence and society course at Olin with a similar framework where we've partnered with 5 different courses. And I know that those integration materials are getting used because I use them in one of my other courses that I've been teaching called software design. The final type of real-world projects I just wanted to briefly touch on is College as a Living Lab. This is an effort that we're doing at Olin, but I think there's similar efforts at a lot of schools. And what I mean by Living Lab is integrating campus operations with the curriculum. So this year I've led the development of an Olin Living Lab course called Building Energy and Operations Optimization. And over the past 2 semesters, we've done 9 projects in collaboration with campus facilities and operations. And one thing I've really enjoyed about teaching this course is how multidisciplinary this course and this problem is. For example, there's someone from my teaching team that does thermodynamics. There's another person that's from campus operations, and the student teams are also super multidisciplinary because this problem can't be solved with one discipline alone. And I'll talk some about my building energy optimization research towards the end of my talk, this ongoing work. More broadly in teaching, I think it's really interesting and important to be involved in the broader computer science education community. So here's a list of some of the recent ways I've worked with the education community. A lot of this is through the SIGSI Computer Science Education Conference. through invited panels or talks or organizing workshops. And I think it's just really important as teachers that we find common community with people at other institutions to see how people are doing things and kind of continue iterating on best practices. So if you haven't attended the SIGSE conference and you teach computer science, I'd highly encourage you to check it out. The next one is just happening in about a month in Pittsburgh. Moving a little bit more towards research, I'm really passionate about research in ways that I can work with undergrads. I think it's a great educational tool as well as a way to contribute to the field more broadly. It's a way that students can see what the field is like today and also work on real world projects and in other contexts. So here's some pictures from my lab at Olin. We've done some paper reading groups. So there's some students doing whiteboard math of a paper outside on a nice day. I took 4 of my students to the reinforcement learning conference, which happened for the first time last summer. There's a bunch of my students and one of my robots. And that was a stormy day last summer when we decided it was time to jump in puddles. So I think there's a lot of fun aspects of doing research with undergrads, both in kind of the community building aspects and also in the educational and research contribution aspects. A lot of my students are also considering grad school as a career path or even applying to grad school right now. And so it's another great way for students to kind of get more exposure to research as undergrads. Now pivoting a little bit more towards my my research goals and impact. I'm a person that comes from a combination of machine learning and robotics, and my dream is really to see robots that can do a really diverse set of tasks and help humans in our everyday lives in lots of different ways. One challenge is that every home is different, and so robots will need to be able to generalize to new situations. And that's where machine learning can be really useful. It can learn patterns from data that help us generalize to new examples. And so I'm not going to spend too long on how machine learning works, but here's one example from computer vision. Imagine that we have an image, which is going to be labeled as either a cat or a dog, and we're going to train a model to predict these labels. The challenge, though, is that in robotics, this one-to-one mapping isn't so clear. So imagine we want this robot to reach the goal. We could train a model that predicts whether it should go left, forward, or right. But the challenge is that we don't actually know whether the robot should go left or right to get to the goal. Maybe both would be good options. So we can't label every step the same way that we could in computer vision. We have to run the robot over multiple time steps and then look at that whole path over time to label whether or not the robot was doing the correct thing. So maybe in this case, going left would give the robot access to the goal. And so we'll give that a score of +5. And if the robot had gone forward, they would have hit this obstacle. So we'll give that a negative score of -1. And it turns out that if the robot had gone right, it wouldn't have reached the goal after all. And so maybe that gets a score of 0. And so to understand how we would train such a robot, we can introduce reinforcement learning, which is a technique that's really good for learning to reason over time. And the nice thing is that humans and animals actually do reinforcement learning too. So imagine that we want to train a dog to play fetch. A dog has to take many actions, like running towards the toy, picking it up, and bringing the toy back. And we reward the dog after it's completed all of those actions. And the dog has to learn which of those actions were important for receiving that reward. And this is a really challenging problem, trying to figure out which of those actions lead to the reward. And to do a little bit more of a hands-on example, we're going to play a little game, which is human reinforcement learning. One of us is going to be a reinforcement learning agent, and the rest of us are going to train the agent to do a new task by providing rewards in the form of clapping. So could I get a volunteer, preferably from the room, to be a reinforcement learning agent?
I'm already a grad student. I get voluntold to do that.
I shall volunteer.
All right.
Not asking you because you might have a similar, but if you'd like to do it, by all means.
Great. So Rebecca's going to be our agent. Could you step outside for a moment?
Okay.
Thank you.
So that I can't hear what's going on?
Exactly. Okay. So the task that we are going to teach Rebecca today is patting your head. Is everyone good on that? All right. Zoom people, if you would like to participate, you can take yourself off mute so that we can hear your clapping as well. All right, so now we are going to train you to do this task, so you can begin exploring.
A little encouraging. Fully encouraging. Would you like an orange? I might pick as a task. Nope. Okay. Maybe she's thirsty. Maybe she wants to. Oh. I don't know. It does feel hard. Feels like I've got to do a lot in order. Maybe I need to give the talk. So we have some materials here. I'm gonna. Oh. I see some clues, but that's cheating. That was literally never gonna happen.
All right, let's give Rebecca a round of applause. Thank you. I really like that game because I think it demonstrates a lot of the challenges in reinforcement learning. For example, it can be really hard to know what are the dimensions that an agent should even explore in this space. Rebecca did a great job trying to figure that out, and also used some nice prior knowledge by seeing the answer on the slide here. Yeah, so I think that this game is really fun, and I like to play this game in classes too. But kind of thinking more about reinforcement learning and what it's good at and what it's not so good at. We've seen a lot of successes in reinforcement learning, from Atari to the game of Go to simulated robotic successes. And this is all in the last decade or so. But on the other hand, reinforcement learning successes haven't really translated to the physical world. For example, the most common household robot today is a Roomba, which can even kind of fail to intelligently move around obstacles, let alone do more interesting things. I argue that the missing piece is physicality. The reinforcement learning successes thus far have been in simulation, and moving to the real world adds really challenging constraints. So let's look at how this physicality can play out in the real world. The first challenge is getting access to high quality rewards. So in Atari games and simulated robotics tasks, there can be rewards at nearly every time step that are guiding the agent. But in the real world, the robot sees little rewards because it's challenging to create such dense labels. There might only be one reward at the end of the trajectory. And so the robot can get stuck, similar to kind of how Rebecca was wandering around and not seeing any rewards, right? It can be hard for an agent to even select actions that collect interesting data, let alone solve the actual task. The next issue is the constraint of training time on real robots. Entirely in simulation, AlphaGo, shown here, was trained for 340 million steps over a period of about 3 weeks. But even with Google operating 14 robots in parallel, it's not approaching that same scale of training. These robots spent 3 times longer collecting data and ended up with 425 times less data. But there's actually a bigger constraint with physicality, and that's in evaluation. One of the best ways that science progresses is through comparison. So we evaluate 2 ideas and iterate based on which of those ideas performs better. So here I have 3 different robotics labs that have each developed their own method for solving a scooping task. But even within this task, the setups vary in many ways. So can you all kind of identify any of the differences between these setups? Yeah.
They're all using different robot arms.
Exactly, yeah, they're all using different robot arms. Yeah, anything else?
Scooping tools.
Different scooping tools for sure.
Things.
Yeah, different amounts of material, different container sizes for sure. Yeah, anything else?
Maybe different strategies.
What was that?
Maybe different strategies. Is one of them using the edge of the container? I can't
It's
quite
cutting
see.
it. Did anyone catch that?
Should I repeat?
Mark, I didn't hear you. Do you want to put that in the chat?
Sure.
Okay, different strategies, for sure. Yeah, they could be using, different angles of approaching the container, for example. Oh yeah, using the edge of the container, and that might be more or less feasible in these different setups, for sure. Yeah, so I mean, my point is just that there's a lot of ways these vary. Some additional ones that I noticed were the camera angle is different. So some of these are more head-on and some of them are more from the side. The lighting is different. So for example, Lab B seems to have more natural light. And all of these can lead to really different results in these types of robotic tasks. The challenge here is that this makes it really hard to compare results across these different settings. Basically, each lab would have to independently implement and tune the methods from all 3 labs on their setting in order to have like realistic results and be able to progress and kind of figure out which method is the best. And this is really limiting scientific progress in robot learning. So in my research overall, I try to make reinforcement learning more practical for the real world and help to overcome some of these 3 challenges. In this talk, I'll discuss kind of one way we can combat each of these challenges. So the first challenge was that reward sparsity problem. Like, not having anyone there clapping for your robot can be really hard when you don't have access to nice, dense rewards. And so one way that we can approach this is by leveraging information from multiple senses. For example, humans don't just see, we also hear. So I'll show how an agent that can use 2 senses together, like audio and video, can help improve the efficiency of exploration. And I call this approach See, Hear, Explore. Second, we'll look at the lack of data problem. So in the limited data regime, pre-training can help an agent to learn more quickly. I'll show how by using these things called contact microphones, by using them as touch sensors, we can leverage internet audio-visual data to pre-train representations for a real robot and hopefully help with that data efficiency issue. And this work is called Hearing Touch. And finally, to tackle that evaluation challenge, I'll introduce a real-world benchmark. So by using shared hardware to compare methods, I aim to not only accelerate progress in robot learning, but also lower the barrier to entry in research, making it easier for everyone that wants to get started in robot learning, but might not be able to implement all of the data collection and robot setup themselves. And this benchmark is called Train Offline, Test Online. So the first 2 directions that I'll talk about today are aiming at making policy learning more efficient by leveraging multiple senses and also pre-training from other tasks. And the last one I'll talk about is how we can apply this to real robots in a benchmarking kind of setting. Can I get a thumbs up, thumbs down on how things are, how you're following things so far? Cool. Are there any questions either in the room or on Zoom before we jump into some of the project details? All right, well, let's jump into the details of See, Hear, Explore to start. Okay, so instead of taking random actions in the hopes of uncovering some rewards in the world, like we were in that clapping game, an agent can create its own rewards to determine what might be interesting to explore. And so by creating its own rewards, the agent can be motivated to explore without external guidance. Then the question is, how should we define these rewards? One way to explore is through something called curiosity. I want to reward the agent for exploring surprising parts of the world. And so let's look at how this might work. Let's say the agent observes this image. Then the agent is going to try to predict what the next image might look like, for example, after it's taken a step forward. And then the agent will take that step forward and see what the real future image looks like. And the agent will compare the imagined future to the real future. If they're similar, then this was not a very interesting thing to explore. And so the agent will only give itself a small reward. But if they're different, the agent is really surprised. And so the agent will give itself a large reward. So this idea seems pretty good, but there are some challenges with where this agent might struggle. For example, does anyone have an idea what might happen if this agent that's being rewarded for surprises encounters some source of randomness in the world? Yeah.
What's if you put it in front of like a television, it'll just get addicted to watching television because it's constantly being surprised by what's on screen.
Exactly. Yeah. If you put this type of agent in front of a TV that's just showing random things, it will indeed, as you say, get addicted to television. So let's look at that, an experiment that shows that. So first, we're going to show an example of an agent without any kind of TV source that's navigating through this maze. So in that example, we could see that the agent is successfully exploring this maze and is able to eventually explore the goal. But now let's see what happens when we introduce the noisy TV. So indeed, just as you had predicted, the randomness of the TV leads to a high reward for the agent watching that TV. This is called the couch potato problem, which I find very entertaining. And the challenge here is that this is an undesirable form of exploration. So we're going to need a way to improve the exploration method. In particular, in this work, we look at how we can use multiple sensory modalities to improve exploration. So imagine the agent is not only seeing this image, but can also hear sounds from the world. One way we could do audiovisual curiosity is by predicting sound from the image. However, you can imagine that sound prediction would still struggle from that same issue with the randomness. For example, imagine that there's a radio that's changing stations in the background. Then we'd have some other form of an audio couch potato in this method. So instead, we designed an alternative form of audiovisual curiosity that uses association instead of prediction. I want to reward the agent for discovering new combinations of audio and video. And instead of asking what sound would occur based on this image, we're asking, can this image and sound co-occur? And the question is, how does the agent know if it's a new combination? The agent is going to start exploring this world and collecting data that's used to learn these associations. And then when the agent encounters an association that has not yet learned, it receives reward for uncovering this new thing in the world. Can I get a thumbs up, thumbs down on this see, hear, explore method?
I'll hear more about it before I decide whether or not I think it makes intuitive sense to me, I guess.
Yeah, if you have a question, I'd love to hear it.
No, I'll just let you.
Okay. Cool. Yeah, let's see if there's any questions in the Zoom chat.
Thumbs up.
All right. Okay. Cool. So let's look at how this performs in some experiments.
There is-
Oh, is there a question?
From more. I'm unclear whether the agent seeks out things that make sound.
Seeks out things that make sound. That's a great question. So imagine that we're in like an environment where there isn't a lot of sound, then it might end up seeking out things that make sound, but it's really only implicitly doing that through looking for new combinations of audio and video. So things that make sound might involve more novelty in the audio-visual combinations, but it's not like explicitly just looking for new things that make sound. Does that answer your question, Mark? Great. Cool. Okay, so let's look at some experimental results from this method. The setting I'll show today is Atari games, which are commonly used in curiosity prior work and also conveniently contain both images and sound. So first I'll show a video of the future prediction curiosity, that first baseline method. And notice that it's going to move the pile rapidly, as this form of randomness can be hard to predict. All right. And now let's look at the see, hear, explore method. I thought it was interesting in that example how it seems like the See Hear Explore agent ends up with lots of back-to-back sound effects. And also, one thing I noticed is that it clears multiple colors of bricks at the same time, which perhaps might lead to new audiovisual combinations. Now let's look at some quantitative results. So here on the x-axis is training time, and on y-axis is the game reward. This game reward is just a proxy for exploration, and it's something that the agent does not have access to during training. So the agent is just being trained on its own kind of curiosity-based rewards, not on the game score. So note that this is a really imperfect metric for exploration. For example, a high game score doesn't necessarily mean that an agent is exploring well. And likewise, a good exploration agent might not actually achieve a high game score. But this is a common proxy in exploration research. And here I'm showing See Hear Explore, which is this blue curve, to two baselines, which are both doing kind of that future prediction style visual curiosity. And we see that in this particular target game, the See Hear Explore agent can much more efficiently explore the space as measured by a more rapidly increasing game score. And we didn't just test this on one Atari game, we tested it on these 12. And we found that See Hear Explore performed better in 8 of those 12 examples. Can I get a thumbs up, thumbs down on the See Hear Explore direction? Are there questions about that? Yeah.
So the See Hear Explore, it sort of exists in order to, or at least how you motivated it originally, was in order to try and get past the couch potato problem, so that if it's just seeing random images, but it's not necessarily getting, you know, audio that goes along with them, it will somehow begin to reject those. I'm wondering, one, by what mechanism does it get past that? And two, what happens if you have something where the TV, instead of playing just random images, play, you know, like the Lord of the Rings extended edition, where it's something where the audio and the video do line up, but it's still just watching a movie instead of continuing to explore the maze.
Yeah, I mean, so I think it doesn't necessarily fully solve the problem. Like if there's a lot of interesting stuff happening in, you know, for example, the Lord of the Rings extended edition, it might still get stuck near that. But I would argue that that actually is an interesting thing to explore because it's not a source of randomness, right? There's still a lot of structure in the combinations of audio and video in Lord of the Rings extended edition. So you could have a model that is learning the distribution of combinations of audio and video. And I think it would learn to move past that more quickly because it's not actually having to predict each frame, which is a pretty challenging task. It's just learning, have I seen things like these go together? So for example, we could imagine a model might pick up on patterns of if there's a face that has a mouth moving, then there might be speech associated with that. And then that could be treated as kind of like, yes, that seems like something I've seen before, and then kind of move on more quickly. Does that answer your question?
But then if you have just the randomness, where it has, you know, picture of a chicken, picture of a fish, picture of, you know, train or whatever, and it's constantly associating those, or constantly finding combinations of that with whatever goes in the background, wouldn't it also just sort of want to look at that all day to find these new combinations?
Yeah, for sure. I mean, you can definitely still have settings where this type of exploration agent would get stuck. Like you mentioned, if there's unassociated randomness in both the audio and the video separately, then that could lead to an agent getting stuck. And I think we saw some variants of that challenge in some of these games, but I would argue that in the world, especially when we're thinking about more real world applications of robotics, that there's usually a lot of structure and kind of correlation between stuff in different sensory modalities. And so I think that this actually is much more practical for settings that exist in the wild. Yeah.
This may have a related answer then, but can you characterize what the properties of the examples where your method didn't do better?
Yeah. So this is something we do in the paper, and I'm happy to talk more about it during our meeting later today too. But yeah, one of the examples was kind of when there's When there's randomness between the audio and the video, that's hard to kind of correlate. I think we saw that in a couple games. I think there might have been 1 or 2 games where there just wasn't that much audio. And so I again would argue that that's not super realistic, that when we think about the real world, that there's much more richness in the different modalities. But I think that was one challenge that we found was, you know, if it's just visual, then this is not as interesting of a form of exploration. Yeah. Are there any other questions, for example, people on Zoom? All right. So zooming out a little bit, thinking about the takeaways from See, Hear, Explore. In reinforcement learning and robotics, there's this tendency to treat additional sensor data in the same way. But See, Hear, Explore shows how learning algorithms can actually take advantage of multimodal data, not just because they have additional information, but because of the structure and complementary nature of this information. And so See, Hear, Explore demonstrates one way that we can make reinforcement learning more practical through efficient training with multimodality. But let's say that we want to apply multimodality on real robots. There's still a challenge in collecting enough multimodal data, and sample efficiency is really crucial when we think about moving to real-world robotics. So let's look at how we can leverage prior data to enable real-world multimodal robot learning. And that's in this work called Hearing Touch. So multimodality is really promising for use on real robots, where complex dynamics and contacts make vision-only solutions really difficult, if not impossible. And touch sensing makes a lot of sense as an additional modality in these real-world robotic settings. But there's a challenge with touch sensors, and that's that we lack large-scale tactile data, and we don't always know how to interpret the outputs from these touch sensors. Enter the contact microphone. Using contact microphones as an alternative touch sensor, we can record tactile data that is inherently audio-based. Contact microphones pick up vibrations from direct contacts, which makes them well-suited to manipulation settings, like putting them on this robot gripper here. They're also really high frequency and really inexpensive compared with a lot of touch sensors today. So this costs $1, whereas a lot of tactile sensors are in the thousands of dollars. And since contact microphones give us audio, we can actually listen to their outputs. So here's an example of how the contact microphone sounds when doing a spatula flipping task. And I have one more example from the zipping task. Isn't that cool? I thought this was really fun. You know, as a grad student that was frequently debugging robotics experiments, it was much more interesting when you could listen to the outputs from your sensors. So in contrast with See, Hear, Explore, in this work, we're going to look at behavior cloning from a set of demonstrations as opposed to reinforcement learning. And that change is basically going to further enable data efficiency for the real world setting. The inputs to the policy here are an image observation, an audio that's in the form of this spectrogram here, and then we're outputting actions to take in the real world. The focus of this work in particular is on how we can pre-train the audio and visual encoders that are going to be part of this overall policy. So for consistency, we're going to use the same image encoder initialization for all of the different baselines. Specifically, it's called R3M, which is trained on large-scale internet data. The differences between our method and the different baselines is going to lie in how the contact audio is used and how that contact audio encoder is pre-trained. So our method is going to use large-scale internet data for audiovisual pre-training. The next method is still going to do audio encoder pre-training, but it's going to use the audio from the demonstration in that robot setting rather than using large-scale internet data. Another option is to initialize the audio encoder from scratch. So we're not doing any pre-training, but it's still going to learn as part of the overall behavior cloning task. And the final baseline is vision only, which helps to evaluate the significance of access to contact audio alone versus the benefits within pre-training or not pre-training and how we're doing that encoder pre-training. Are there questions on how we're setting up this problem with these different types of method comparisons. All right. So we're going to evaluate these different encoders with behavior cloning on 3 different manipulation tasks, flipping, scooping, and zipping. And for each of these tasks, we're going to collect about 50 demonstrations, which is what the behavior cloning is going to learn from. At evaluation time, we're going to learn from, we're learning from these train objects, and then we're going to deploy it on these unseen test objects. So we've got like some different bagels, we've got a different candy and different containers for these scooping containers here, and then different lunch boxes that we're going to zip over there. So here we have the results showing the success rate for each method on these 3 different tasks. So our method, which is again doing internet pre-training of the audio and the visual encoders, is shown in blue, and it performs the best on average across these 3 tasks. One thing that was really surprising was that the green bars, which represent initializing the audio encoder from scratch, actually performed better than the in-domain audio pre-training. One thing that this suggests to me is that the distribution of data available in the in-domain pre-training was rather small because of the small number of demonstrations in these set of experiments. And the vision-only baseline, which is shown in red, performs the worst on average. In fact, it didn't succeed at all on the flipping task. Are there any questions on this hearing touch approach or the results here? Let's see, I think there's a question in the chat. Is unzipping harder than zipping? That's a great question. We didn't do the unzipping task here, but I think I would be curious to know whether that's true. My guess is that they would be similar difficulty. So for context on the zipping task, the gripper already has the zipper in its parallel jaw gripper at the beginning of the episode, and so it doesn't have to actually find the zipper or anything like that. And so I'm guessing it's more about following the trajectory of the zipper route, which I think would be equally challenging with unzipping or zipping. Let's see if there's other questions. Let's see. The expert sound data is clear or with noise. So I don't know whether the audio was coming through super well. It seems like there might have been some static on the speakers in the room, but maybe it came through okay on Zoom. Our paper website should have the audio for those tasks too, so you could listen to it there if you were interested. But generally, we're not actually explicitly adding any noise to the sound data. What is the y-axis on these charts? So the y-axis is the kind of reward or success rate, which we had to a little bit set up for these different tasks. So for scooping, it's the weight of material that's scooped. For flipping, it's just a binary task of whether you succeeded or failed. So this is more like a success rate rather than a reward. And for zipping, it's a great question. I think zipping might also be some kind of reward. I think it might have been based on the distance traveled along the trajectory. The details are on the paper, and I'd be happy to look those up afterwards. And those are all kind of human annotated during the rollouts. All right. So zooming out a little bit on this hearing touch work, my takeaway was not just that contact microphones are interesting as a touch sensor for manipulation, but also that using audio-based touch sensors actually enables this large-scale multimodal pre-training that wouldn't be possible with kind of new types of sensors for robotics that we don't have access to a lot of data for already. So we've seen 2 ways to make robot learning more practical through efficient training by using multiple senses and also leveraging prior data for pre-training. But even with this really efficient training, the evaluations for a project like the contact microphone experiments involved a lot of late nights, as something that a lot of grad students in robotics can relate to. So now I'll show how the train offline test online benchmark allows users to share hardware for evaluation across institutions and hopefully get more sleep at night. So specifically, we're introducing this benchmark called Train Offline, Test Online, which we abbreviate TOTO. In the TOTO framework, we're providing a real-world data set that's collected on our hardware. And remote users can locally train agents of their choosing using this data. They would submit these policies for evaluation on our hardware, which is located at Carnegie Mellon. And then the evaluation can guide future iterations of method development for that remote user. And finally, those evaluations also form a joint leaderboard, which is giving direct access, direct comparisons on shared tasks, data, and hardware. And as I mentioned in the beginning with those challenges, this is something that could take someone entering the field a really long time to set up. So they would have to do a lot of data collection on their own. They'd have to do a lot of software engineering to set up this robot platform and the robotic stack, and iterate on the task definition, for example. And so this framework makes things a lot easier for that remote user. For example, we have this really large training data set containing these two tasks, scooping and pouring. We have about 2,000 scooping trajectories and 1,000 pouring trajectories. I speak from experience that this is a lot of time for any grad student. And so being able to share this training data and also have a paired evaluation setting can really save a lot of time for someone at another institution that doesn't have these type of resources. One thing to note is that the distribution of training data is much larger here than in the contact microphone experiments. So for example, we have varied objects, locations, lighting conditions, etc. And note that the reward definition on these two tasks is just similar to the scooping task from contact microphones. It's the weight of the material that is successfully scooped or poured. So we can think of robotics as having two main components. One is perception, and then the second one is action. Using TOTO, we can ask questions of each of these two components. So first, we can ask, what makes a good visual representation for robot learning? And to answer this, we are going to train behavior cloning policies on top of different pre-trained image encoders, somewhat like we were doing with the audio encoders in the contact microphones work. And we're going to evaluate all these policies on the same shared hardware, and the results will inform us about what kind of representations work well for robot learning. And these methods, we evaluated 5 such representations, and they were all contributed by 5 different labs. So this is really exciting, being able to have these experiments that are all tuned by the people that created these methods on the same hardware platform. So here I'm going to show example rollouts from 2 of these different representations. First, let's look at something called MoCo, which is pre-trained in domain on the TOTO data. So believe it or not, MoCo performed the best of the 5 representations that we evaluated. Here we're using Starburst as the test material. That was an intentional choice to not choose a messier material on the part of the people that were doing these experiments. And now let's look at R3M, which is generically pre-trained on the large-scale Ego 4D dataset. So we found that the more generically pre-trained encoders in this setting didn't work as well. This is somewhat in contrast to the finding we had from the Hearing Touch project. But again, remember that the in-domain data has much more variance in it in this case. So that's why we hypothesize that the in-domain pre-training works better in this case because of the scale of training data available and the breadth of that training data. The second set of experiments in TOTO focuses on the highlighted policy part of the pipeline. So we can ask, what's a good method for offline policy learning, potentially with the vision model as consistent across all the methods. So we had 4 different remote labs contribute methods to the initial TOTO benchmark, and we evaluate them again on the same shared hardware. Here are some of the quantitative results for policy learning. So here we're showing the success rate on the y-axis. So this is a 0 to 1 thing. And in the blue bars, we're showing the method's performance on the training location. So, the cup was in this position and we saw that in the training data, and we're going to put it in that position again and roll out each of these methods and see how well they do. But the more interesting thing is how the methods perform on the test locations. So these are unseen object locations at test time. And we find that all methods have a pretty large generalization gap. So they're able to do the train locations, but many of them are not able to do the test locations super well. This is especially true for this approach called VIN, which is doing nearest neighbors. So it's selecting actions based on the nearest neighbors from the Toto training data, which unsurprisingly works very well on the train locations and very poorly on the test locations. It doesn't achieve any success on the test locations. And let's look at an example of how that played out. So we can see that it did find a nearest neighbor, but unfortunately, it was not close enough to the unseen test location to really achieve any success. And that was true across all of the different test locations. Another thing to note is that we found that this DT method, which is on the right, didn't achieve any success on train or test locations on this important task. But after the users that submitted DT compared their method with the more successful methods on this benchmark, they were able to modify their approach and really improve their results. And so the exciting thing here is that by having all of these methods contributed by different institutions, we can now really more quickly iterate on how methods work on this type of benchmark and learn from each other's institutions without having to independently implement and train and test everyone's methods. So I think this is really promising for accelerating progress in robot learning. And one thing that I'm particularly really excited about is that all of these different labs had undergraduate contributors to this benchmark, which is another sign that this type of benchmark can make robot learning more accessible and kind of reduce some of the barriers to entry. So an undergraduate might actually be able to do some method iteration rather than spending their entire first year doing robotics research, collecting data, or trying to get our robot to work. And we also ran a competition at NeurIPS, which is one of the premier machine learning conferences, on this benchmark. And similarly there, the majority of teams had undergraduate contributors, which is something that I'm personally really passionate about. Are there questions on the Toto benchmark?
So if I understood correctly, you're allowing these remote users to control your robot platform. Just wondering sort of how you addressed security or training concerns, so whether accidentally or maliciously, there might have been people trying to harm your setup.
Yeah, for sure. We thought a lot about safety for this. For the benchmark, for the competition that we ran, which was more likely to be people that were less familiar with robotics or, people that we didn't necessarily have an existing collaboration with. We had a simulation round before the real world deployment. So they had to kind of demonstrate that they could train a policy that at least performed based on above some minimal threshold in the simulation round before they qualified for the real world round. And we also weren't allowing direct real-time access to the robot. So there was someone there all the time when supervising the behavior with all the normal like emergency stop functionality that you would have with robot experiments. Yeah. Other questions on Toto?
I would just remark, there was a thing at Georgia Tech that was kind of similar where they had like a bunch of little robot guys rolling around on the floor, and you had a camera pointing down and you could, tell them how to, coordinate themselves. So just something kind of related.
Exactly. Yeah, I think that's called the Robotarium. And The Robotarium's awesome because they also do a lot of curricular integration. So they also work with a lot of, undergraduate robotics courses, and it's got a little bit more of like swarm functionality application. But I totally agree that there's a lot of similarities with, remote access to robots as a way to reduce barriers to entry in the field. And at one of the benchmarking workshops that I organized around this robots in the cloud space, we had a speaker from the Robotarium project, which was great to hear from. Yeah. Other questions on the Toto front? All right. So zooming out, the takeaway that I had from Toto is that by using shared hardware, we can make robot learning evaluation much simpler and also more comparable, which is really helpful to the field in multiple ways. And so overall, thinking about my research more broadly, I really care a lot about real-world transferability and also accessibility of the field. See, Hear, Explore, and Hearing, Touch were helping to move us more towards practical, efficient robot learning, while the Toto project is working more on the evaluation and deployment of these kinds of methods and making them possible on a broader scale. Looking forward, I'm really excited about continuing to work on improving benchmarking and robot learning because I think it can make the field look pretty different. So for example, research won't be limited to people that have the resources to afford real robots or those that have robotics expertise. A computer vision researcher with no hardware experience could conduct real-world robot experiments, or even a high school student could try it out. It would also be much easier to have experiments on real robots in more papers. So we wouldn't have this ongoing discussion in robotics about whether simulation results are sufficient for publishing a paper, because we would actually be able to much more easily get these real world results into many more methods. And finally, when everyone has access to the same hardware and the same training data, anyone can show that their method is the best. So it won't be the labs with the resources automatically have state-of-the-art results just because they had the robots and the training data to train their methods on. In addition to expanding access to robot learning, I'm really excited about expanding the definition of what we mean by robot learning. So according to the NSF, a robot is defined as intelligence embodied in an engineered construct. And at the beginning of this talk, I said that the most common household robot today is a Roomba. But actually, if we're using an expansive definition like this, I would argue that the most common household robot is the house itself. Buildings are robots. They have sensors and actuators, especially when we think about their heating and cooling systems. So for example, this is a screenshot from the building that my office is in right now at Olin. You can see there's lots of different sensors, a lot of temperature sensors, power meters, etc. There's also actuators on here. So we have 2 fans. We also have some actuators here that are controlling how much air is going through in different parts of the system. This is an air handling unit, which is just one part of a much larger complex system that does building heating, cooling, and ventilation. And as it turns out, building energy optimization also faces a lot of the same challenges as robot learning challenges that I've described so far. There's physicality constraints in terms of deploying models, both in terms of safety and the logistical side of all the software infrastructure that you need to develop in order to implement these models. There's also real challenges in accessing large data sets on building energy, especially for students who might just be learning about the field. It can be really hard to get access to this type of data. And that's why I'm really excited about bringing similar benchmarking with open source data sets to problems in building heating and cooling. So one of the efforts I've been leading over the last year at Olin is to open source our building data. And building data has all these different types of trends, and it's over several years, and it's trended usually every 5 to 15 minutes. So there's actually a lot of data here and a real richness that I'm excited about. And this is a benchmark that's actually being led by a Columbia PhD student named Judah. And so we're leading this kind of multi-institutional benchmark that currently has 11 different buildings in a bunch of different campuses. And so this is something that I'm really excited about because it allows us to learn from a much more diverse set of data, and also just like provide access to people that might not have, for example, ongoing collaborations with people in a campus operations department. So I see collaborations between departments and institutions as a really crucial part of this building energy optimization work. Another reason that I'm really excited about robot learning for buildings is the potential impact in addressing the climate crisis. I found this really surprising as someone that doesn't have a lot of background in the environmental side. But buildings contribute almost 40% of greenhouse gas emissions in the US, with commercial buildings being about 17% of that overall number. And about half of building emissions come from heating and cooling. So here I'm showing a bar chart of Olin's measured emissions from our climate action plan. And specifically, these two bars alone are pretty much exclusively heating and cooling. This one being natural gas usage from our boilers, which are used for heating, and this being purchased electricity, the majority of which is used for cooling and air conditioning. And so I think having people working on this type of problem is going to be really important for addressing the climate crisis, and not just kind of building new sustainable buildings. We also have to really grapple with the fact that we have a lot of existing buildings that need to be made more efficient. Another reason I'm really excited about building energy is that it can help expand the view of what we think about when we think about robots. This is a quote I really liked from a student who took my course in the fall. The extensible, adaptable definition of a robot has completely overhauled my outlook on what being a robotics engineer means. And I think that's great. I think there's like a lot of preconceived notions that especially undergraduate students might have when they think about what robotics is as a field. And so being able to show them this really impactful application that they can see and live in and also has climate implications, I think is really exciting. I'll leave you for my vision for robot learning as a whole. I'd like the field to have a diverse set of contributors, including undergraduates and people from less well-resourced institutions. So I think diversity in robotics means new perspectives, ideas, and applications. So with this diversity as a foundation, we can bring robot learning to lots of real-world applications, not just creating things like home generalist robots, but also making transportation safer, or cleaning up waste, or supporting sustainable agriculture, or improving power grid operation. And there are so many applications that we've barely scratched the surface of. And I'm excited for the newcomers in the field to think of even more. And with that, I'd like to thank all the wonderful people that I've worked with over the years, especially on the work that I presented today, my collaborators, lab mates, interns, and mentors, and especially the undergraduates who taught me how to be a better mentor and led me to this undergraduate institution career path. And with that, I can happily answer any more questions.
Questions? There's a couple that came in on the chat while we were talking. You want to look at those?
All right, let's see.
One was, I think, just before you switched into the building.
Oh,
topic,
got it.
and one during the building topic, both from Mark.
Okay, let's see. I'll look at the building one first. Interesting that there don't appear to be more presence sensors, so you don't have to cool or heat in empty spaces. Actually, there are a ton of those. So the air handling unit is central, but we do see a lot of occupancy sensors in more individual zones within a building. And I ran a project on that in the course in the fall. So for example, a lot of the office rooms at Olin have occupancy sensors. I think there's some really interesting questions that would be good to address with people from a bunch of different backgrounds, especially people in HCI or people from humanities about security and privacy when thinking about different types of sensing in buildings too. Let's see, and then Mark's other question, Henry Minsky's Alila.ai, which uses what he characterizes as Piagetin learning. Can you talk about possible benefits for that approach? My intuitions are that some basic ontology for the task, e.g. object permanence, and some knowledge about properties of solid versus liquids could only help. Yeah, I'm not super familiar with that specific approach, but I definitely agree that having some kind of task ontology would be really useful, especially when we think about getting access to even larger robot data sets. And there's been some of these in recent years. But when we have larger data sets, then multitask learning can be much more effective, especially if we have some information about how each of those tasks might be related to one another. Yeah, are there other questions? Yeah.
This is less a question, more just a generalized comment, but you mentioned that you were working with the actual, people who work for the building when doing a lot of the, reinforcement learning for efficiency stuff. And I just think that, getting in, more practical knowledge to these sorts of more academic projects. I think that that's really undervalued in the general case. You know, for example, you can think about, you know, car manufacturers, maybe they should bring in, you know, mechanics when actually designing the cars, that they can say like, hey, this thing is going to be impossible to maintain. Can you please, you know, fix that? So I think that that's a really valuable approach. The question, other comment that I have, I was making notes to myself,
Nice.
is are you familiar with video game speed running at all?
A little bit. Yeah.
Yeah, so it seems like a lot of the stuff when it comes to you know, exploration,
Mhm.
you know, trying to come up with ways to you know, optimize against an environment, being able to say, you know, okay, here's something where it's a difficult task, it's something where, you know, the optimal way to do things isn't necessarily something that is obvious just based on the test that's given to you,
Mhm.
as well as it being, you know, a relatively mature community where there is a ton of existing data in the form of, you know, video records. So I just think that, you know, going towards that, especially like with the sparseness of the rewards, because you're not rewarded, you know, until you actually get to the end and you know, log the final time. I think that could be, you know, something that would potentially have some value as yet another simulated benchmark. If it doesn't really help anybody.
Yeah, for sure. And I think there has been some recent effort on like using YouTube videos of different video game plays for, you know, creating data sets that people can learn from. And I definitely agree that I think going forward, I wouldn't do as much exploration from scratch and would really rely on more existing sources of data like you described.
Great, thank you. So in the interest of time, I think we'll stop it there. Students who are on Zoom or in the room, we have time at 3:30 today up here in Milstein 514 for students and Victoria to get a chance to talk, and we'll provide cookies as well, so feel free to come by for that. And with that, thank you so much.
Everyone.